So thanks for coming, everyone. This is the beginning of the 2022's IBiM semester. We are very pleased to invite Dr. David Derive to give a presentation on the energized mass insight to fluid forces on accelerating bodies. Dr. David Derive is actually my postdoc supervisor. He received his PhD degree from TU Darmstadt. After that, he go to the MIT to continue as a postdoc associate. And he initiated his professorship at the University of Calgary. After that, in 2014, he go to Queen's University, and right now he's the associate professor at Queen's University. Dr. David Derive's research is mainly focused on the bio-inspired fluid mechanics. He's not only distributes his ideas in professional seminars like IBiM, but he also distributes his research to public. For instance, if you check Dr. Derive's website, you'll find that there are 2 videos recorded by the Discovery Channel and CBC on the bird flies and rotors. So, being said that, I will left the platform to Dr. David Derive, and you can begin. Thanks.
Thanks a lot, Kai. It's a great pleasure to share some thoughts and work with you today. And yeah, it's very nice to have you, Kai, as the host, even though we haven't seen each other in a few months now. So welcome. I'm going to talk about something called energized mass. Before I get started, make sure I can, there we go. I want to give credit where credit is due. So I've had 2 very talented PhD students work on something related to this over the last years. Josh just defended his PhD a few weeks ago, and John already a couple of years ago. And the other person I'd like to give credit and is my colleague Gabe Weymouth. Many of you know him, University of Southampton, and he's been quite inspirational and helpful in this journey. I assume everyone can see my cursor, right? So if we start out kind of the history of this interest in this talk today, which I've tried to keep very general and broad rather than overly focused. Many years ago, I remember even sitting in some defenses and seminars on perching more from the perspective of controls. And there was work done like this, which I believe was at UPenn, but I could be mistaken. And more specifically, this work now almost 10 years ago on perching of fixed wing small scale flyers. And it was a very interesting study, but the fluid mechanics side of it would be arguably considered underdeveloped. And when I say underdeveloped, the fluid mechanics, it's when you go easily into, you walk out the door every day and you watch the maneuverability and ability of small biological flying animals to perch, to maneuver, and their ability to do it is obviously considerably much better than anything that we're still able to do today. So if we look at a perching small scale flyer and you slow it down, and we did some reconstructions about this from multiple views, one thing that's quite interesting is that it's basically a ballistic process. So it falls towards its target. And then at the very last minute, there is a rapid deployment of its feathers and a rapid change in area, which is its own topic in its own right. But that rapid deployment of its feathers essentially initiates what we always refer to as added mass, and something that is extremely ubiquitous in all biological propulsion and control of biological systems. In fact, most biological systems at inertial Reynolds numbers have a degree of unsteadiness, and with that comes this so-called added mass effect. So if you look in water, you see just as many examples of changes in area and changes in shape that relate to the added mass effect. And if we look across different species and scales, it seems to be apparent at all levels. So if you focus in, and I hope the video isn't too choppy, if you focus in on the webbed propulsors of this frog that we collected, you can see very clearly how the webbed foot changes dramatically in area and shrinks again during its propulsive stroke. So this has been studied quite a bit. And in fact, my colleague Gabe Weymouth has done some very nice work on cephalopods. But I want to focus today first on sort of a very basic review of added mass theory and discuss a little bit some of the contentious points. And this is a contentious issue, I'll say it right now, because I have many colleagues who have worked on this topic from the perspective of, let's say, a vortex impulse description. And some have shown very nicely how added mass or potential flow added mass theory can work in real viscous flows. And so with this, I just want to talk about its origin, show some of the work we've done, and then talk about a different perspective. And it's just like anything in fluid mechanics and aerodynamics, we can explain a phenomenon from several different perspectives, and they're complementary. So added mass has a long history. I think the word says it all. It's also described as apparent mass or a virtual mass or a non-circulatory force. And this effect was observed by sailors and many well before the description was formalized through potential flow theory. And basically, if we just step back for a second and imagine the simplest situation, let's describe all the kinetic energy in our fluid with no bound integrate over some infinite volume as K. And then we can take this kinetic energy of our fluid surrounding a body of interest, and we can normalize the kinetic energy of the fluid over this volume by the actual body velocity squared, where big U is the instantaneous velocity of our body of interest within this bounded fluid. So when we rewrite it in this manner, we can say that in a steady translation, in a potential flow, we know that there is no net force on a body moving at steady velocity through a D'Alembert's paradox. And so with that, we can expect that the total amount of kinetic energy around this moving body at big U will be a constant. Now, we're not interested in the steady condition, we're interested in an acceleration of the body. And so if you consider an acceleration, you take the time rate of change of this term K, and you can show that this is directly proportional to the additional work that the body will apply onto the surrounding fluid. So if the body accelerates from rest, it is imparting work on the fluid that is surrounding it over time. And once we settle on this arrangement, it's very easy to show that this force, this so-called added mass force, is then directly proportional to the body's acceleration time through this constant of proportionality, which we refer to as the added mass or added mass coefficient. And so this is essentially looks like something like a mass, even though this is a very contentious business using the word mass, because we know it's a little more complicated than just adding a suitcase to your car and driving onwards. So in potential flow theory, you can go through the derivation for a number of bodies and derive the added mass coefficient matrix. And so, for instance, I've picked a few very simple cases because we'll discuss them today. A sphere, the so-called added mass is equivalent to half of the volume of the displaced sphere. And for the case of a circular plate, you get another very simple expression like this. This is for the added mass coefficient normal to the acceleration. Sorry, parallel to the acceleration axis of acceleration. So in a potential flow, we know that a body moving at a constant speed will have, let's take a cylinder or a flat plate, a 2D flat plate in this case. And we know that the pressure distribution is, and for that matter, the velocity field is symmetric front to back. And when the flow is symmetric front to back, there's no net drag. So in an inviscid flow, we have no net drag on a constant moving a body with constant velocity. Now, when you accelerate this body at some time, you actually, through a potential flow, through this change in the rate of change of the momentum, you can show that there is an additional term known as the added mass force. And in a time invariant system, as treated in a potential flow, you can show that the velocity field in your system can be scaled through this function g of x relative to the body's velocity big U of t. Once you go through that exercise, you can replace the simple force balance and express the added mass force in as simple a manner as possible, where in the end you derive this so-called added mass coefficient. Now, what's really contentious and what I want to bring attention to here is the fact that the term, for instance, in a 2D flat plate, the coefficient is proportional to a circular body of fluid with mass rho, so with density rho, that essentially accelerates with this plate. Now, we know in practice, of course, that this is ridiculous and that the fluid is not, the fluid that's accelerated with the body isn't limited to this circular body, but rather it's affected at infinity. On the other hand, it's a very practical way of looking at this problem, and it's intuitive, even though when we look at this at first glance, we say, okay, let's never mention this bounded circle ever again. I'll come back to this later because this is sort of the point of contention. So is this assumption of a time invariant system reasonable in a viscous flow? Because after all, we're interested in viscous flows and all the nuances associated with them. So let's break this down. This is my way of looking at the world. Maybe I have very poor vision, but essentially all our biological systems at inertial scales can be broken down into a series of plates and bodies of revolution, right? And so whether it's an aircraft with a fuselage and wings or something else, essentially these are all either sharp plates or spheres. And so let's consider to start with the canonical case of a circular plate accelerating from rest and the formation of a nice vortex ring behind this plate as it accelerates from left to right. Similarly, you can do that for an accelerating sphere, where on an accelerating sphere from rest, you go from essentially in a symmetric velocity field to a strong asymmetry where you form a vortex ring that pinches off this body of revolution. So let's imagine a bumblebee is now a sphere and a couple plates that are accelerating relative to one another. And if you look at the flow field, so these are some PIV measurements at the edge of this plate and also over the surface of the sphere. Again, the flow is coming from the right. So you see for the circular plate from the edge, you see something that qualitatively looks self-similar in that we know the vortex will grow in time and in space. But for a circular plate, it actually stays on for up to something like 10 body diameters. And so over that long acceleration process, you can still see the vortex grow in strength, but more or less stay in the vicinity of the plate. And so it kind of looks sort of the best case scenario in that it's sort of like a time invariant system. That vortex stays with the plate and this outer streamlines remain constant in time. For the circular spherical body, I should say, accelerating, it's a little more interesting because the separation line will move. So you have this viscous region on the body, and then you have the roll up of this shear layer on the aft side of the body as a function of the instantaneous Reynolds number acceleration. And this vortex ring, as I'm pointing to here, will then roll up and shed. And so the system is far less simple, let's say, to describe during acceleration. So let's go into testing what I will call the potential flow added mass concept, the one where we assume there is a coefficient of proportionality that is invariant in time. And let's test that out on a series of simple cases. So for instance, the simplest and most favorable test case will be this circular plate that we accelerate because we have a fixed separation point. And for all intents and purposes, the flow that sets up looks sort of invariant in time, at least for many diameters. The vortex ring forms and it stays with the plate in time. And in these experiments, I'll come back to these many, many times again, we essentially have a large tank of water where we accelerate a test article. We measure the forces at the body surface or at the body attachment point, and we do either particle image velocimetry or particle tracking velocimetry, depending on the situation. I'll show both today. So let's consider the very simple case of an accelerating flat plate from rest, where we show the drag coefficient as a function of normalized time. So the force at 0 is 0. We then hit a peak measured force. So the blue is actually directly from experiments at around the end of the acceleration process. And once we hit that peak, we have this so-called relaxation process, where the force returns over a number of body diameters or characteristic length scales. It returns eventually down to the steady state force coefficient for a circular flat plate. Now, if this were to be a potential flow, we would multiply the constant acceleration, which we have more or less in our experiment, times the coefficient of proportionality, the add mass coefficient for this geometry, a circular plate. And what we get is something, and this is all very qualitative in nature, but if you bear with me, we get something that goes from more or less 0 to a constant. And then when the acceleration is done and the body moves at a constant terminal velocity, this term would drop to 0. Okay. Then what's done historically out of convenience, out of practicality, is to say, okay, let's also include the steady state drag coefficient that's obtained empirically for a viscous flow. So we know that for a circular plate, the steady state drag coefficient has a value on the order of 1, let's say. And so you add this red line, superimpose this red line to the blue line, and you get now this sort of combined estimate of the total force. What really interests us at a first approximation is how close can we come to estimating that peak force, that maximum force that's generated during the acceleration phase, because after all, that's sort of the limit in terms of what the system can generate. So what we're going to look into now is how far off are we from estimating the total force when using this relatively simple breakdown of an added mass coefficient plus the steady state drag. So the other thing we want to study and explore is the effect of the initial condition. So usually we talk about added mass in the context of a body accelerating from some simple quiescent condition from rest, for instance. And so if we consider that case in a viscous flow, the flow initially at rest is quiescent and it's symmetric. And so we have a pretty good idea of how things will set up. But what happens, for instance, if we have a body, the same body now moving at a terminal velocity, which then experiences the same acceleration? Will it have the same force response through that same relative acceleration, or does the initial condition play a role? And so we're going to consider both of these cases, and we're going to consider the fact that in a potential flow, it's always symmetric, right? So it doesn't really matter. There is no nuance between an initial condition at rest or an initial condition at some higher velocity. So again, we have this experiment and we prescribe a number of normalized accelerations. So the acceleration moduli goes from a maximum of 4, which is, you can barely see. So you go from rest to a very rapid increase to a terminal velocity here of u over u1 of 1. And then at some later time, once you hit quiescent conditions, you jump again, apply the same acceleration, and you hit now a terminal velocity that is twice that of the initial terminal velocity. These lines here represent then the whole span of accelerations that we attempted, from the most aggressive to something that's more and more quasi-steady in nature, so relatively low accelerations. And if you look at the initial force plot, now we're normalizing the forces using the first terminal velocity u1. If you look at the force response, you get what everyone likes to call the added mass spike or peak from the acceleration. And then if you have a slightly milder acceleration, the acceleration takes place over a longer convective time. We've seen this many, many times before. You get this sort of decay of the peak and shift to the right. Once you finish the acceleration, the forces take a number of diameters to relax into what we would consider steady state. So you can see here we're as far as almost 20 convective times before we hit the so-called steady state condition. And then at that time, we apply again another series of accelerations that are effectively the same, but with a different initial condition. So it gives us the opportunity to compare apples to apples. We're applying exactly the same acceleration to exactly the same geometry. The only difference here is that in one case, the initial condition is rest, and the other case, the initial condition is a separated flow, that behind a circular plate at steady state. So on the top here, you will see results obtained from experiment from PID, and on the bottom are simulations run through Gabe's water lily code. And qualitatively, and again, a lot of this is qualitative, but I think it makes the case. We can look at two terminal Reynolds numbers. One is 125,000, the other is 250,000. Because of course the initial condition for this one is 0, so we go from 0 to a Reynolds number of 125,000. Here we go from a Reynolds number of 125,000 to 250,000. But what we see here is that we have both in the experiment and in the simulation, not surprisingly, the formation and position of a vortex that grows. So this is initially the formation, and then at some later distance, about 1 diameter downstream, the vortex has expanded, diffused, and moved a little bit relative to the plate. The same is observed qualitatively at the second initial condition, where you're starting from a separated flow. And in that case, you see during the acceleration process, the roll up of a new vortex, despite the fact that in the background, you have this separated, nasty turbulent wake. And again, we see qualitatively that second formate roll up process is again, more or less the same in both these cases. Okay, so it gives us some confidence that the simulations and the experiments are in reasonable agreement. So we want to figure out now, how close can we get to the estimated peak force, measured or simulated peak force, by simply adding the potential flow added mass force to the steady state, quasi-steady or steady state drag in parallel. And this is a bit tricky to digest, but essentially what you see here is, again, the force peak, so the highest force that we measure or simulate, as a function of different acceleration moduli. So if you look at the blue dots, the blue circles, these are discrete experiments where the force peak that we measure is increasing more or less linearly at some point, up until this acceleration module support. Our experiments simply cannot go any faster without breaking the whole rig. Whereas in Gabe's case, in his simulations, he's able to artificially run simulations to higher and higher, almost non-physical accelerations, if you will. And what we're able to show here is that the steady state contribution, of course, is constant regardless of the acceleration, but that, of course, the added mass contribution to that peak force will grow linearly with the acceleration modules, not surprisingly. When we take now the total force, the peak force that we measure or simulate, and subtract the peak associated with added mass and that of steady state, and we normalize it by the peak, we get the residual force, the error. And what you observe for the initial condition from rest is that at lower acceleration moduli, you have errors that approach 40%. And they decay, they reduce over time, not over time, but over higher accelerations, but they asymptote towards an error, a residual that's on the order of 20%. So even at the most impulsive motion that is more and more inviscid-like in nature, you still have a residual or a discrepancy on the order of 20%. And what's interesting now, if you do the same analysis, but when you're starting with your initial condition with a separated flow, in that point, your error, if we focus on the error or the residual force, is actually lower to some extent at the same acceleration moduli. So if you look at an acceleration modulus of 2, the relative discrepancy is smaller. It's now on the order of just over 20%, but it asymptotes at higher and higher acceleration moduli still to a similar value. And this has bothered us and is contentious because you would expect qualitatively that at the limit of both of these cases, at the highest and highest accelerations, you would get something that behaves more and more like a potential flow. So there's something missing, or we need a different way of looking at this problem. So with that, I'm going to jump into reviewing this concept of a drift volume that several people have explored over the last decade or two in great detail. It's a complex description, but I'm going to keep it as simple as I can. And let's go back to this crude and erroneous description of atom mass being a fluid region colored in blue that is equivalent to a cylinder of fluid bound to our body that's accelerating through our body. And I know this creates a lot of contention and upsets a lot of people, but if we just naively look at this and imagine how we would explain this to a first-year student, an undergrad student in an intro fluids course, you know, maybe there's something intuitive about this that's worth considering. So let's see, how bad is this idea in its own right? And Darwin, at the end of this article is, you know, 70 years old. This Darwin is the grandson of the original Darwin that we all remember. They had this sort of passing comment at the very end of their article, an analogy regarding the cartwheel. So in other words, you have a cart, I guess back then maybe a horse drawn, a cart with wooden wheels is a more appropriate description. But we imagine this wheel traveling over time and picking up mud in the path and drawing it over the wheel and dropping it at a later time instant. And you can say, yeah, but that doesn't really matter whether there's mud on the wheels or whether the wheels are dry. It really shouldn't affect the system. And of course, if you think of this as a quasi-continuous system, you can say you're constantly picking up mud and you're constantly depositing this mud at a later point. But you are physically transporting mud from your bike tire, or whatever analogy you like, or from your shoes from point A to point B, without necessarily incurring any penalty, if you will. So if we consider Newton's second law for a time-varying system, you can, and this is where things get ugly, but you can say qualitatively, well, it's not really the atom mass, but this is some fluid that we're dragging along with us. And if you describe a second law in a time-varying system, you have two terms. One is what looks sort of like the added mass term that we know from potential flow. And then B, you get this additional term, which is the rate of change of mass or rate of change of fluid that is affected by this motion. And it's that additional term that we have to consider going forward. So in the Darwinian drift, you have these nice descriptions. You have essentially, you tag a bunch of fluid on a plane, you pass the body through the plane, and at some later time step, you have this shaded volume of fluid that has been dragged. This is the mud that you've dragged along with your body. That's what we call a drift volume. There's this beautiful GIF that I found, and I still don't know who generated it. Maybe somebody can tell me, but essentially, if you tag this line here, and this is a steady translating ball or sphere in a potential flow, you see very beautifully this drift volume stretch to infinity. And you see, more interestingly, these orange points here represent the elastica. If you follow their trajectories, these elastica represent the bound of this drift volume over time. Okay. So if we kind of get into this mode of thinking about fluid being dragged with our body and say, okay, what happens in real life when we're dragging fluid with our body in space? We don't typically describe our experiments or our fluid dynamics problems like this in any way. We can actually measure this, right? So if we tag all the fluid in our experiment and track it using PTV, we can tag all the green fluid that originates on a plane, and we can show, and I hope the videos are not too choppy, so I hope you can get something from this. You can see some fluid that goes backwards, but most of the fluid, of course, is dragged forward. And we can say maybe this is a way of looking at the same problem, but from a different perspective. So out of curiosity, we tagged all the fluid that ended up in the vortex. So with tracking, you can play God. You can say, color all the fluid that ends up at a later time step over here. And so in this case, we tagged orange was all this fluid that at a later time ended up after the acceleration inside the vortex core. And you can see in this visualization, it's not ideal, it's not perfect. You can see though, qualitatively, how much the fluid upstream interacts and is transported and engulfed, mixed into the vortex wake, if you will. So it's a much more complicated process than we probably would like to believe if we're going to assume something like an added mass, potential flow added mass description. So yeah, engulfment is important. It's a complicated process. Let me finally end with this business about energized mass. And it's just another perspective, perhaps one that helps us, perhaps one that confuses us, but nevertheless, here it is. So we measure flow, we can tag fluid particles around our body, and with a tracking technique, we can identify their motion, but we can also, of course, identify their net kinetic energy. So here we're coloring all the fluid around our sphere on a central plane as it accelerates we're normalizing that kinetic energy of the fluid by the body velocity u squared. And so we know that the kinetic energy of all the fluid in an unbounded system can be described with K, and then we can normalize that kinetic energy here, this value of K, we can normalize that by the body velocity u squared, rearrange slightly and say, hey, there's actually some unbounded amount of fluid in our system that is being energized over time. And this fluid is moving essentially on average with the velocity of the body. Okay. So this is our definition. So it's not inferred from potential flow, but it's measured directly. And therefore we can say that the force on our body through Newton's second law for a varying mass system is nothing other than the time rate of change of this energized mass times the body velocity plus this instantaneous amount of mass that has been energized times the acceleration of the body, where the latter term looks a little bit more like the traditional added mass description. So when Gabe ran some simulations in the body fixed frame of reference for an accelerating sphere, the vorticity field is what we all typically like to look at. You can say, yeah, this is not a particularly simple problem to handle, but that's, I guess, the beauty in trying a sphere, because you have a moving separation line and a much more complicated starting process. But if you look at the kinetic energy field, and this is not the greatest video, it's kind of confusing. It's certainly not something that we're used to considering in our formulations. So we did some experiments. We measured the drag. We did PTV measurements so we could track the fluid in time. And when you're considering an accelerating sphere, you are strongly dependent on whether your terminal velocity is supercritical. In other words, if you're down here with these dark blue, light blue lines, you're in the supercritical regime, or whether you're relaxing after your acceleration to a subcritical regime. So we picked Reynolds number 50,000 and 250,000 as two terminal velocities. And we also then tried a number of different accelerations. So we had a most aggressive acceleration from rest, and then a medium, and then a milder acceleration. Okay. And of course, this process, as I mentioned before, is not self-similar. So you have this formation and roll up and shedding of this vortex ring during the acceleration, during and after the acceleration of the body. So qualitatively, if you measure the kinetic energy on these tagged particles, you see that both for the subcritical acceleration up to a subcritical Reynolds number or up to a supercritical Reynolds number, you see that at first glance, after the acceleration is complete, that you are affecting a cloud of fluid most significantly within, let's say, a radius of your body. Now, of course, you're affecting and energizing fluid at infinity in theory, but in practice, most of the fluid that's affected or the contribution to the total kinetic energy is most pronounced right in the immediate region and wake of the body. So when you have this problem, you have during the initial acceleration, you energize fluid, not just downstream, but also upstream of your body. Everything is you're applying work to the system of fluid, if you will, from body to fluid. And then as time progresses, that energized fluid or energized mass diffuses, advects away from the body, such that eventually you start shedding this energized fluid into the wake, and you continue to generate more from the surface, just as you would in a description using vorticity. So if you measure all the kinetic energy in your system as a function of time during the acceleration process, this is the subcritical case, we can show that, yeah, you can measure the kinetic energy as it jumps up during the acceleration process. And then you can more or less, and this is, there's some challenges in doing this. There's some noise, of course. You can measure this gradual increase in the kinetic energy of the system as you are moving them in steady state. So you have to imagine, for a body that generates drag in steady state, you have to still add more and more kinetic energy to the fluid, because that's the penalty of drag. Same can be done for higher, hitting a supercritical case. And what we wanted to do qualitatively was look at, okay, if we measure the forces directly, so here's a peak. Let me focus best to the highest acceleration. So you have a peak force due to the acceleration, and then you have a relaxation, and you have some noise, and you have some readjustment, but more or less you're dropping down to what you would call steady state eventually here. You can measure all of the kinetic energy in the system and show that, yeah, if you apply that approach, you can get a good estimate. And most importantly is using this concept in some very basic modeling, which I don't have time to describe today, you can get a reasonable estimate of the jump up and then the relaxation to eventually the steady state conditions. In the end, this is not the best test case from what we've seen, but it gives us some idea of how we want to maybe pursue this idea in the future. I'll end just with a few thoughts about this Lagrangian perspective. Maybe it's interesting for some of you. If you consider the acceleration of these, again, subcritical cases, so you're accelerating from rest to a subcritical Reynolds number, or you're accelerating from rest to a supercritical Reynolds number, for a lower acceleration modulus and for a higher acceleration, and we show them to more or less synchronize with each other. What we're doing here is we're visualizing all the fluid as a function as how much that fluid has been displaced in the axial direction. So fluid that is more or less white or more or less invisible is barely dragged. The mud is barely dragged from right to left. And to that point, it doesn't contribute significantly to the drag on the system. However, fluid that is tagged red is displaced significantly from right to left during the acceleration and subsequent motion. And in plotting it and visualizing it this way, measuring it is the first challenge, of course, we can see that there is fluid upstream that is in particularly affected and imparted into this wake at a later time. So it means that we have sort of a cause and effect relationship between fluid that we are about to hit and how it later contributes to the amount of drag in our system. So this is the time equals 0 before the acceleration, and this is fluid that we color based on how it later rolls up into the shear layer and contributes to the total amount of drag. So for a subcritical case, we see the sort of larger body of fluid, wider, if you will, and you see these ridges, and these ridges are essentially blobs of fluid that entrain or are not entrained, but are drawn into the shear layer and at a later time into the wake. So here's at a later time step, that fluid that we initially had tagged upstream is then dragged into the shear layer. And we can see then at a later time step yet, all that fluid then being engulfed and brought into the wake region. So by toggling back and forth in this sort of perspective, Lagrangian perspective, I'm hopeful that in time we can draw new insights and possibly even new ideas in terms of how to control the flow manipulate the flow, or at least understand how biological systems possibly do this to their advantage. With that, to keep things succinct as much as possible, I'm going to stop and take any questions or feedback or criticism for all those who are not a fan of beating up added mass. I don't think my goal here was to beat up added mass or potential flow added mass, but so much as to just draw attention and promote discussion on the topic. Okay, thank you.
Yeah, thanks, Dave, for this super clear talk. So, I know Josh's work, but like it's never been so clear. So it's time to questions. So if you have any questions, you can just open your mic, or you can left the message in the chat, or raise your hand. Any questions? Yeah. If no one has a question, I actually have a question, Dave.
Yeah, of course.
Essentially, that drift volume, even we use Lagrangian methods to measure the drift value, it's actually very challenging. Also, it's very to write the code and to do the post-processing is quite complex.
It is, yeah.
Did you ever consider to based on your measurement, or based on the measurements you observed in the experiments, is there any possibly some empirical relation, say, or for this kind of for instance, sphere shape, or for the circular flat plate?
Yeah.
Any empirical relation you can predict the drift value
It's a very good question. And suggestion actually, and maybe the way to do this. I think if you look at the original concept for potential flow is your body displaces through this plane, and you get something that looks like connular I don't know how best to describe this, but yeah, let's say it's a cone of influence. So a region of fluid that you can describe possibly with some simple function. What's a little bit tricky for me, but I think that's part of the fun in this, is there's still a lot of possible avenues to take. If you look at something like this, the drift volume is then a cone, and we don't have data right in where the sting is, so this is a problem. But the drift volume is also described by the influence that this vortex ring has on the surrounding fluid. So you could argue that the drift volume is this circular path around the vortex and this connular shape that originates back at the plane of interest. And maybe by adding the two, or by having a description of how much that vortex entrains fluid over time, you could do something like that. And that would be beautiful, because it would give us essentially like a correction, like you're saying, right, Kai?
Yeah, I think it's
because ultimately it's all about having a low order model, something that you can do on the back of an envelope, and something that you can easily apply, and not so much something that requires doing these really complicated experiments. You know about this is better than I do, because you did your own Lagrangian measurements and tried to right in this facility. So it's very challenging, and it's very painful, and it requires some not everybody wants to get into that. So I think it's a great idea, and possibly something that we should pursue, or somebody should pursue in a future study.
Maybe you can even predict the birth perching, just model is like a flat plate. Of course, it's 3D, and if you can solve the drift volume, is maybe I think it's a good direction, maybe.
Yeah, certainly if you have that additional influence. The only thing is there's this entrainment. So these vortices are very effective at churning fluid. I think I showed it in this video here. If you tag all the fluid upstream that goes into the vortex at a later time, it's complicated, right? I mean, you have this mixing, and across the shear layer, you have this entrainment process, if you will. And the rate at which it entrains fluid is a function of Reynolds number, it's a function of acceleration, it's a function of other parameters. But maybe at a first approximation, we can come up with an expression for that. Yeah,
Correct.
That's a really good idea.
Correct.
Good idea.
I noticed like in the chat, there's a person who wants to ask a question. You can just open your mic and ask the question.
What's that? There first, Ignacio has a question, but he didn't write it. So maybe Ignacio, you want to turn your microphone on?
Sure. Can you hear me?
Yeah.
Can you hear me?
Yeah.
Fantastic. Well, thank you very much for the presentation. It was very impressively clear given the complexity of the subject. So that was awesome, really. Can you go back to the slide where you compare the peaks experimentally and numerically computed versus the, I think the acceleration?
This one here?
Yes, exactly. Yeah. So I'm a bit puzzled by the fact that even for an infinite acceleration, you will still have an error, and the fact that there seems to be agreement between CFD and experiments.
Yeah.
Because I think that once you accelerate instantaneously, if you accelerate, for example, with a step change of the velocity with an infinite acceleration, you can only change the velocity field, but you cannot move any particle, and you cannot move vorticity, for example. So the only thing you can do is instantaneously you can change the velocity everywhere. So that can only be a potential flow phenomena. I wonder how can there be a problem.
So I know, yeah. So first of all, I mean, this point here from the experiment is very challenging to do properly. We can go a bit faster, but at some point you're more likely to oops, where am I? Going back here. Yeah, so an acceleration modulus of 4 is an extremely aggressive maneuver. If these plates weren't made out of stainless steel, they would be just crushed. And so indeed, if you double that and you go to 8, so up here somewhere, at that point during the acceleration, I agree with you. The vorticity doesn't have a time to diffuse and roll up and form a vortex or anything. So in fact, this inset here shows you qualitatively how much that vorticity has, even at that plate edge, had a chance to roll up in that region. And maybe we're still far, far away from that quasi-impulsive case where it is really perfectly impulsive, where maybe we have to go to an acceleration modulus of 100 or something. But even so, you still have the generation of vorticity. As soon as you have you're imposing no slip. In the real world, you have no slip. So even in this, at the moment where you accelerate at the edge of the plate, you have to satisfy the Kutta condition. And in that region, I mean, you could argue, well, that's just a small region of the plate. It can't contribute significantly to the forces. But even that small nuance perhaps contributes enough to the formation or generation of vorticity. It hasn't had a chance to diffuse outwards, but it's still, if we do a vortex impulse description of this problem, it still contributes to the force. And I would say if these were just based on our experiments and we were doing this at extremely high accelerations, that I'd say the experiment is wrong. I don't trust the experiments, and we throw the data away. But Gabe's code, and many of you might have already read about it. It's quite impressive. He ran this several times. We had to actually triple check just to make sure that this wasn't some type of error. And indeed, it's physical. So I don't know. I agree with what you're saying, actually, that it's sort of it's counterintuitive, and it doesn't make sense that you would have a chance to have anything but a potential flow-like response. But at least up until this acceleration modulus of 10, it still seems to be off by something on the order of 20%. Regardless if you're starting from rest or if your initial condition is that of a separated flow. So I don't know. I don't know if that answers your question, Ignacio. That's a really good question. I hope one day we can come up with a simple explanation for this.
Thank you very much. We'll take it maybe offline again.
Yeah.
Thank you.
Yeah. Let's talk about it soon. I think that's a good idea. Thanks, Ignacio. The other question, if I jump, wondering what you would think this would look like at very low Reynolds numbers, like 0 to 1. And then the other one, how do you think flapping oscillator might exist entirely in high cost region where they are constantly accelerating fresh counter-rotating vortices? Yeah, see how these are related. So, you know, in this sort of intermediate region where you're neither in inertial flows nor in a traditional Stokes regime, there certainly will be this bizarre yet significant effect. And I mean, why would we want to assume a potential flow description for something at arguably more and more viscous-like behavior? So if you're at a Reynolds number of 10, let's say, or 1, certainly potential flow added mass coefficient wouldn't be something worth applying, at least in my gut feeling. I've never actually tried it. So I think, yes, we would benefit from having some type of description like this. And there's no reason, if this works at a Reynolds number of a few 100,000, like we've shown, it certainly will work qualitatively or quantitatively at a Reynolds number of 1 or 10. As long as there is some degree of inertial effects in the flow and it's not perfectly Stokes flow. The other question from Brett was, yeah, how do you think flapping or oscillator organisms might exist entirely in the high cost region where they are constantly accelerating fresh counter-rotating vortices? I mean, if you're a biological system and you're really clever, you, as was shown with the cephalopod escape maneuver, and that was more recently published in Science Robotics, I think, from Gabe's group. If you're very clever in how you manipulate the accelerating fluid to your benefit, I can imagine situations where you come out ahead. I mean, biology always seems to impress us with its more clever use of unsteady aerodynamics or hydrodynamics versus how our human solutions have, I would argue, failed. Another question was, interested in the chain of water disasters. Rainfall causes the river to rise, which in turn leads to the instability of embankments, which in turn leads to urban waterlogging. Now I hope to simulate changes in flow speed, energy, and volume will process. Can you give me some suggestions of what I should consider in my study? How can I consider added mass in water disasters? Thank you. I don't know. I guess if these processes are erosion can be described as the impact of waves or high, essentially you have this strong deceleration of fluid as it impacts these embankments. I can imagine that process would be very rich. I have no experience with this topic, but again, it would be something, I would imagine some hydrologist, some experimentalist, somebody has looked at this problem before, but to look at it under a lens like this, where you were able to somehow track the motion of the fluid and how much fluid is, or how much mass is eroded from the surface in time, could be really interesting, because there would be some type of energy balance that would, or force balance that would result in this interaction between fluid and solid. Yeah, sounds interesting. I mean, we can talk offline about that in the future. Let's see if there are any other questions. Okay, seems like I answered some of those questions at least. What do you think, Kai? Is that good enough?
Yeah, thanks, Dave. Thanks, Dave, for taking my job. Yeah, it's very excellent. Yeah.
So, no, it's good. I'm glad there's some questions. Hopefully it's been at least colorful and promoted some thought. I'm not trying to discourage anyone from taking the vortex impulse descriptions. There are some beautiful papers published in the last 5 years that that reconcile potential flow added mass and the viscous vortex wake descriptions. They're certainly very, very lovely pieces of work. They provide their own challenges from an experimental point of view, and their own challenges in terms of how to generalize this to other bodies or general shapes. But this is just one flavor to try today. Okay.
Yeah, thanks, Dave. It's about the time. So this is probably the end of the seminar. Thanks for sharing your idea.
Yeah, it was a pleasure. Thanks for everyone for joining wherever you are, and I look forward to staying in touch. See you.